Hello everyone, I'm Lin Hu from Peking University. I'm very glad to introduce our work, Accelerating Triangle Counting on GPU. I'm going to introduce our work by four parts. Firstly, the introduction, then follows two technical sections, and finally is our experiments. Triangle counting is a well-studied problem on GPU. In this work, we aim to propose a unified strategy to optimize multiple existing triangle counting algorithms by pre-processing graph data. While we implement graph algorithms on GPU, we face two challenges: workload balance and resource diversity. Here we will explain them by introducing GPU architecture. Please see the figure. The left part shows software level structure of GPU. Programmers launch kernels, which are also called grid. A grid contains many blocks, while a block contains many warps. A warp is a basic running thread group because threads in it are running in SIMT manner, which means that code branches in those threads will cause some threads in idle until all threads finish their works. In graphs, the length of adjacency lists for different vertex varies a lot. The workload of triangle counting tasks is closely related with length of adjacent lists. Therefore, workloads of threads inside warp may have large difference. That will cause severe performance decline. The right part of the figure shows the hardware architecture of GPU. Here SM is short for stream multiprocessor. We can see that SM is an independent unit of GPU, which has its own computing and memory resource. Generally, we hope that those tasks we assign to one SM could fully use both computing and memory resource. We have an observation that workloads of vertex in graph algorithms usually have different resource preference. Undesigned workload dispatch of vertex to SMs usually leads to skewed resource needs of SMs. Luckily, we found two pre-processing strategies that provides us opportunity to fix these two problems. Those are edge direction and vertex reordering. Generally, for triangle counting tasks, we first transform undirected graph to directed ones to avoid duplicated computation. Given a graph, different edge directing strategies lead to different out-degree distribution. Therefore, leading to different workload of threads inside warps. In almost all triangle counting works, blocks acquire consecutive vertices as workloads. So vertex reordering definitely change the workload distribution of blocks as well as SMs. And the table shows shows performance difference of different pre-processing strategies. As we can see from the table, the same datasets have different performance under different pre-processing methods, which show that a better pre-processing method is necessary. To figure out how this pre-processing strategy work on the final performance, we propose two quantitative analytic models based on those patterns. There are some heuristic pre-processing method before, but as far as we know, we are the first to use quantitative analytic models. Next, we define the cost under different pre-processing strategies, and lastly, we give our solution to find optimal pre-processings. Firstly, I will introduce our edge direction section. Synchronization is an important pattern in GPU. GPU is a massive parallel hardware, and to assure this consistent access of multiple threads, synchronization is often needed. Here we briefly introduce two state-of-the-art triangle counting methods and analyze how synchronization is used. Please see the following figure. The left figure is a graphic example, and the middle figure shows its adjacent list of this graph. In this implementation, triangle counting is carried out by a bitmap-based set intersection. The right figure shows how we count all triangles containing vertex 9. Vertex 4 and 5 are assigned to two threads. They are responsible for the adjacent list intersection with vertex 9. Those two threads firstly set bitmap of vertex 9's adjacent list and then do the intersection. To ensure the consistent access of the map, a synchronization is carried out. The next implementation we use wedge to count triangles. A wedge contains three vertices U, V, and W. To tell whether U and W are neighbors, W is searched in the adjacent list of U. The adjacent list of U is copied to fast access memory for better performance. Similarly, to assure a consistent memory access of this copied pattern, a synchronization is also necessary. In fact, synchronization is a common pattern in triangle counting on GPU. We abstract an intra-block PSP model to summarize how synchronization works, as shown in the following figure. Triangle counting process consists of many supersteps, and each superstep are formed by global operation and separate works. The total time of superstep is determined by the threads of largest workloads, and we want the maximum workloads of each threads group to be the smallest possible. In other words, we want the workloads as balanced as possible, considering the overall workload is a constant. Naturally, we define the cost of each edge direction method as follows. The cost of a vertex U is present by the absolute difference of degree U and average out degree in the graph. And the cost of the graph is the sum of all vertices cost. Intuitively, this cost function also requires balanced out degree. Next, we need to find the optimal edge direction solution according to this cost function. We prove that this is an NP-complete problem in our paper. Thus, we aim to propose an approximate algorithm. Firstly, we draw the conclusion that vertices with degree smaller than average out degree can be firstly determined without any affection to the optimal results. We define all their edges as outgoing edges, and that is definitely an optimal result. The proof is given in our papers. Then we give an algorithm accordingly. Our algorithm is a peeling process. Firstly, we peel out all vertices with degree less than average out degree and edges connected to them. The edges are directed as their outgoing edges. Then we repeat the peeling process until all vertices have degree larger than average out degree in the remaining graph. Then we raise the threshold of peeling and keep the process until the whole graph is processed. Algorithm 1 shows our parallelized edge direction method. To accelerate the peeling process, we perform this process on GPU so that the pre-processing will not become a burden of overall triangle counting algorithm. And our approximation algorithm is proved to have a satisfying approximation ratio. It's below 1.8 on both real-world graph and synthetic graphs. This proof is also provided in our paper. Next is our vertex reordering part. Binary search is widely used for list intersection in triangle countings on GPU. According to many works, binary search is more efficient on GPU than sort merge because larger degree of parallelism, better memory access pattern, and less work complexity. So we use binary search as basic computing pattern and analyze its resource prereference. We found that binary search has different resource prereference distinguished by adjacent list lengths. Please see Figure A. A work with 4 threads is doing binary search on a short list and a long list. On the short list, the required data of 4 threads can be fetched in one memory transaction, while on long list, binary search tends to access scattered partition as the search performs, and 4 memory transactions are needed. This leads to different proportion of memory access memory access and computing in a fixed time window as shown in figure B. In a fixed time window, binary search on long list spend more times on memory access, but that on short list could coalesce memory access, so more time is spent on computation. So we conclude that binary search on short list is computer intensive, while on long list is memory intensive. Resource pre-reference leads to resource waste, as shown in the following figure. 3 blocks have different resource pre-reference. The memory needs of all vertex in block 0 they dominate the resource, leading to waste of computation resource, while computation needs dominate block 2, and block 1 have balanced resource needs. Few resources are wasted, and it surely has the best performance. Considering that we want both computing and memory resources in each block are in balanced usage, we give analytic optimization goals as follows. We use FC to denote the computing intensity of vertex, and FM denotes the memory intensity. The CI and MI denotes the overall computation needs and resource needs of a block, respectively. We use lambda CI minus MI to represent the wasted resource in each block. Because C and MI are not under the same measurement, so we use a parameter lambda to break them. I will talk about parameter determination later. And the overall cost is the sum of wasted resource in each block. And our optimization goal is to find the optimal reordering method with the least cost. We give a proof that this problem is also an NP-complete problem in our paper, and we provide a heuristic method. Our method is basically a greedy method. Firstly, we process memory-dominated vertices with which memory access needs surpass the computing needs. We build a minimum heap of all blocks according to sum of memory access intensity of blocks or vertex inside those blocks. When we determine which block or vertex belongs to, we take the block from the heap top, pull the memory-dominated vertex in it, and pull the block back to the heap. All memory-dominated vertices are processed in this way, and the computing-dominated vertices are processed in a similar method, as shown in algorithm 2. We have mentioned that FC and FM represent computing intensity and memory intensity respectively, and we get those two parameters by experiment. We use memory bandwidth as memory intensity and computing throughput as computing intensity, which can both be measured by NVIDIA profiling tools such as NVProf. Lambda is a key parameter that breeds C and M. In fact, it can be regarded as a ratio of maximum task unit determined by memory capacity and that determined by computing capacity. It can't be directly measured, and we design a one-side pressure test to measure it. If task 1 is memory dominated and we force a little more computation pressure to it, the overall time will remain unchanged because computing ability is not fully used. But if we keep increasing computing pressure, it will reach a condition where both resources are all in balanced usage, and we call this balance point. And we keep raising computing pressure. The overall time will increase immediately. We will recognize balance point according to this rule. And at the balance point, we have the equation that MEM equals lambda PC multiple C, where PC refers to computing pressure. That's how we determine lambda. In experiment, we use 5 state-of-the-art implementations to verify the effect of our method. We don't change their implementation, and we carry out experiment on original input graph and our processed graph as comparison. Here we refer to our analytic method as A direction and A order. Here we use one implementation as example. We compare the experimental time with and without our preprocessing method and show its effect, and both our preprocessing strategies apply to it. We compare our eddy direction method with three other methods: ID-based, degree-based, and Keycore-based. Keycore-based direct edges using Keycore decomposition. We use degree-based method as baselines because it performs better than ID-based, and Keycore-based direction process is too time-consuming. We can see from the figure that our method performs well. It achieves 12% to 35% acceleration on kernel time. And because our high-performance eddy direction implementation on GPU, the total time, which includes the preprocessing time, also have good performance. We compare our method with several state-of-the-art vertex reordering method, and we achieve 9% to 48% acceleration on kernel time, and 6% to 31% acceleration in total time, as shown in the table. We combine the two preprocessing together, and the performance is better than we use single preprocessing method, as shown in the figure. That further proves the effect of our method. And our preprocessing method on other 4 implementations achieves similar results. And due to time limitation, I will not introduce them in detail here. My presentation finishes here. Thanks for your listening.